Good morning, welcome, or good morning, good evening, good night, whichever is applicable. Welcome to the second main session. And this session is, as you can see, on the problem of molecular structure, a problem that is absolutely central to the philosophy of chemistry. It's been there from the beginning. It's been discussed by people like Hans Primas, Guy Woolley, and many other papers have appeared since. So without further delay, Vanessa would like to present, and you can see the title right there. Over to you, Vanessa.
Perfect. Thanks so much, Eric, and thanks Olympia and your whole team for this wonderful conference. You know how much I wanted to come to Buenos Aires last year, but unfortunately, hopefully another time I will get to visit. So this is the talk we submitted last year, and when we did submit that, it wasn't yet published, but now it's out, and so it's more, and it's a bit more, so you can find the paper published in the BJPS, but in the presentation, because it's been now a year, we tried to also not only present the main thesis of the paper, but also provide some further kind of insights and answers based on the comments that we've received, you know, this whole time, this past 12 months. So it's a bit of a renewed version in a sense, but there's the main gist of the paper is also presented. So the paper is about the problem of molecular structure, which, as Eric said, is a very important problem, if not one of the most important problems in philosophy of chemistry, because it's related also to the question of whether chemistry is reduced to quantum mechanics, right? And about the metaphysics of chemical entities and properties. So what we did with Alex when we both worked in the meta-science project is kind of look at how the problem of molecular structure is informed and related to the measurement problem. And we concluded, and we claim in the paper, that actually a large part of what we call the problem of molecular structure in philosophy just is the measurement problem. Okay, perfect. So of course, a lot has been said before in the philosophy of chemistry literature about how important quantum mechanics is in describing chemical entities and properties. Physicists and chemists have done a lot of work in not only you know, building these models for different types of chemical entities and providing descriptions, but also in overcoming potential problems they had in calculating specific chemical entities and properties. Yet I think that in philosophy, even though all this has been taken into account, there is still ample room to further disseminate these scientific results and include them even deeper and strongly in the examination of philosophical claims. So the goal of the paper was to show how considerations of on the measurement problem, but also in particular of the solutions to the measurement problem, can kind of contribute to the discussion of issues in philosophy of chemistry, and mostly with respect to chemistry's relation to quantum mechanics, but also with regard to the nature of molecular structure and to the identity of molecules. And I'm going to discuss that a little bit at the end as well. So the plan is to briefly present a little bit what we call the peculiar case of molecular structure. So what is it about molecular structure that make us wonder about it philosophically so much? And I'm going to present the distinction between resultant and configurational Hamiltonians there. And then Alex will take on by presenting the measurement problem and see how the measurement problem actually applies and relates to the peculiar case of molecular structure. And he's going to show that problems of molecular structure just are the measurement problem. And then we're going to go into the implications this has to philosophical problems, not only with respect to chemistry's relation to quantum mechanics, but also to more general metaphysical problems about chemical entities and properties. So let me present a little bit this peculiarity of molecular structure. I feel that almost everyone here knows about this, so I'm not going to talk a lot about it. So we based our, so as Eric said, a lot of people have already talked about this. There are different formulations of this peculiarity by Woolley and Primas, by Eric and Olympia as well. But we decided in the paper to focus, to present it in terms of Robin Henry's distinction, just out of simplicity, because I think that's a very clear formulation of the problem. So the problem is between the distinction of resultant and configurational Hamiltonians. And a Hamiltonian is called a resultant when it takes into account all the physical entities and properties that comprise the molecule and all the interactions that are taken, that occur within them, right? And the resultant Hamiltonian is defined in contrast to configurational ones, because configurational Hamiltonians, unlike resultant, make ad hoc assumptions about the system that is examined through the Schrödinger equation. So the configurational Hamiltonian, most notably, makes the Bohn-Oppenheimer approximation, freezes out the nuclei, and presupposes essentially in that way part of the structure of the system that it's supposed to describe in order to derive all the other chemical properties. Whereas the resultant Hamiltonian doesn't do that, right? It starts from first principles. Now, there are two questions here about this. The first one is, why aren't resultant Hamiltonians used to describe molecules, which, as it turns out, that's how things are. And secondly, how is it rather, that configurational Hamiltonians manage to describe molecules? And this has to do with the first question becomes more evident by looking what we call isomers, right? I'm not going to explain isomers. Everyone here, I suppose, knows what isomers are. So the problem with resultant Hamiltonians is that they give the same description, quantum mechanical descriptions, for all the different isomers a particular collection of atoms and electrons can take, right? So if I were to, if a collection of 8 carbon atoms and 8 hydrogen atoms were to ask the resultant Hamiltonian, which one am I from all the isomers, right? Am I styrene? Am I cyclooctatetrene, or any of the other possible isomers? The resultant Hamiltonian would say, well, I don't know. I look the same for all versions of you, right? I cannot tell you which structure you're going to take. And this is the problem with resultant Hamiltonians. Now, why has this been important in philosophy? Well, because this has been taken as evidence that the quantum mechanics doesn't reduce all chemical facts about molecules, because it doesn't reduce molecular structure. So this is taken as a failure of Hegelian reduction, because certain facts, and specifically structural facts, cannot be derived by quantum mechanics. And some philosophers have taken this even further by claiming that actually this is evidence of not only non-reduction, but of emergence and pluralism. And here, as an example, the most notable example perhaps is Robin Hendry's strong emergence of molecular structure. And this has been spelled out, as you know, in terms of downward causation. So it's been claimed that the inability of resultant Hamiltonians to identify structure is evidence that molecular structure emerges at a level of ontology that actually determines how the lower level is going to behave and interact. Of course, there are other also replies to this. So for example, Primas argues that, well, actually this is evidence that quantum mechanics is in fault here, because it's either not complete or it is just false. And that's why we don't get all the chemical facts that we need from the quantum mechanical description. And Eric as well has talked about this. And I think this is the closest existing reply to our kind of reply to this problem, because he has said that, you know, this is the instance of the problem of the collapse of the wave function, which, however, can be resolved if we appeal to decoherence. Now, we agree in the interpretation here of what the problem is, but as you will see by Alex's analysis, decoherence is not sufficient in order to explain why the problem occurs, right, and how it can be resolved. So I will give the floor to Alex now to talk about the measurement problem.
All right, awesome. Thank you, Vanessa. I hope everyone can hear me. Can you? Yeah. Okay, great, awesome. Okay. Does this work? Can I? Yeah, okay, great. Here we go. Here's our paper. You can find it, the BJPS. So in our joint paper, we argue that the use of resultant Hamiltonians is a special case of the measurement problem. And the kind of key argument depends on this idea that it has the same form as the measurement problem. I'll get to that in a second. It involves a way of thinking about this as analogous to a kind of symmetry breaking, that the resultant Hamiltonian corresponds to a more symmetric state and configurational Hamiltonians correspond to less symmetric states. And that's how we can kind of think of Schrodinger's cat being in a kind of superposition of being dead and alive is this, in a sense, more symmetric state. And something, in order to resolve the measuring problem, needs to break that symmetry between the dead and the alive cat and end up with one or the other. And that's the same kind of form as the problem. And then that's not just enough, that would be to say something like these problems are analogous. But then what we go on to do in the paper in detail, and what we'll sort of gesture at here, is that they have also the same array of solutions. So the claim is that if one, and we do not urge upon you any particular interpretation of quantum mechanics, we don't claim the quantum mechanics measurement problem has been solved, but we suggest that the putative solutions that are out there, in particular the kind of three mainstream ones that are commonly discussed in the philosophy of physics literature, that these can provide an explanation for how we've transitioned from resultant to configurational Hamiltonians. In a sense, they can kind of show you how the symmetry between the different possible states is broken, and we end up with one or other isomer. And given that in principle it looks like these set of solutions can also resolve the problem in the same kind of way, it looks like we therefore have a basis for supposing that these are just instances of the same problem. Okay, good. So what's the measurement problem? Sure, lots of people know what it is. So what I'm really gonna, this sort of comes from Maudlin, this nice kind of trilemma. There are three different options. The wave function of a system is complete. So there's nothing, there are no hidden variables or anything like that. The wave function evolves according to a linear dynamical equation. That is, there is no kind of special collapse dynamics that comes in, and measurements have determinate outcomes. So there aren't many worlds, there's just one type of thing that comes out. Why are these inconsistent? The reason that these are inconsistent is because standardly, as we all know, quantum mechanics can give rise to describing systems in superposition states. The linearity of the Schrodinger equation tells us that there should then be macroscopic superpositions, and macroscopic superpositions seem to be incompatible with single determinate outcomes of the kind we get when we actually do quantum mechanical experiments. So, there we go. Okay. So how does this relate to resultant Hamiltonians? So the claim is that something like the completeness of the wave function describing a system corresponds to describing a system in the basic sort of eigenfunctions of the resultant Hamiltonian. These are a complete description. If there are no hidden variables, then these are all there is to say about the system as it is, assuming that there's no kind of violation of the linear dynamical evolution, then it looks like we have an incompatibility because we observe particular isomeric configurations. Okay, so it looks like we've got a problem of the same form as the measurement problem. It looks like we can describe, or we can think of, in some sense, the resultant Hamiltonian, eigenfunction of the resultant Hamiltonian, corresponding to very, very complex superpositions of all the different possible arrangements, of all the different possible molecules and non-molecules that are made up of this set of particles. Why do we observe one particular isomer? That's the question. So now, is it a problem for this view that there are unequal superpositions of structures that we should expect to find in general, you know, states corresponding to much more likely to find one particular isomer than another? What we say to that is that the problem of resultant Hamiltonians is highly theoretical. So it's a problem about, as I just said, how we get from asymmetry, from symmetry to asymmetry. Now, if this is an in-principle problem, how do we get from symmetry to asymmetry? It looks like resolutions of the measurement problem can address this and help resolve it. If it's a particular problem about particular cases, then in particular cases, the initial conditions will often be asymmetric. So we never start out with the resultant Hamiltonian in the first place. And so it looks like the problem doesn't even get off the ground. one might also worry that we've kind of taken some unbelievably complex mathematical description and pretended we can divide that into different isomeric structures. And what we say to that is, this is just more reason to think this is like the measuring problem. No one thinks that we can really take the unbelievably complicated entanglement of a cat with a measuring device and divide that into an alive and a dead cat state. What you need is a whole complex array of decoherence theory and other ideas in order to get that out. But in principle, if one thinks and follows the maths in the right kind of abstracted way, it looks like you can get to macroscopic superpositions, and there's where the problem comes in. Okay, why do we observe only some structures and not all possible ones? Why do we only observe some particular arrangements of atoms and not all possible arrangements of atoms? That is a really difficult problem. That is an open question. And like I said, we're not advocating for any particular resolution of the measuring problem. So it's the case that this is an open question, and that people, for example, like Wojciech Zurek, think that this problem involves some kind of what he calls quantum Darwinism. There are lots of different types of answers to this type of question, but it's a really, really tough question. We don't think, however, that noticing that this question is difficult undermines in any way the identification of the measuring problem with the problem of the molecular structure. In fact, we think this bolsters our case, because we think that these kind of decoherence and similar kinds of strategies are the right ones to help us out in this kind of context. Okay, so I'm just going to talk quickly about the ever interpretations. I don't think I have time for the others. Yeah, Vanessa's agreeing.
About 2 minutes.
Okay, good. So take the ever interpretation. That just says that when you've got some kind of macroscopic superposition, decoherence ensures there's effective non-interaction between our kind of emergent worlds. Same kind of way, we might say that if we start out in this kind of massive superposition corresponding to an eigenstate of the resultant Hamiltonian, we can then, through decoherent, end up with kind of emergent worlds corresponding to each particular isomer, which we observe in each particular context. And this tells us then, and I just don't have time to go into this, this tells us that we ought not to think of isolated molecules as having structure on their own. In general, isolated molecules may just be in superpositions of structures and not have determinate structures until they come into contact with the environment. Okay, I'm going to hand over to Vanessa to conclude.
Okay, thanks. Oh, wait, you went a little bit too far. So, okay, thanks, Alex. I wish we had time to go through the other interpretations as well, so you can compare the different metaphysical implications of each interpretation and why it is therefore so important to think of the interpretations of quantum mechanics in this context, because each one implies different things about how we understand molecules and their structure, right? So under some interpretations, it turns out that we don't have structure in isolation. And if that is indeed the case, if that follows as we claim from the interpretation, then this first has direct implications on the question of reduction, because now there's no longer the question of whether quantum mechanics can derive molecular structure, because it becomes moot, that question. There is no structure to derive in the first place. So there is no failure of reduction, strictly speaking, under certain interpretations. And this opens the room to kind of revive reductionist theses and review them in a different way. Of course, again, this is not a set of questions, and I don't want to strongly advocate for reductionism, but it does leave a room open for it. And even if you want to advocate for emergence, yes, I'm stopping now. Even if you want to advocate for emergence, then again, this will become contingent on the particular interpretation you're going to assume, because again, certain interpretations such as the Everettian one, and especially if you look at David Wallace's work on weak emergence of the multiverse, right? So there are certain understandings of emergence which can be accommodated, but within specific interpretations of quantum mechanics. And the second implication has to do with the nature of molecules. you know better than anyone as chemists that structure is a defining property of molecules. And the interesting question therefore is whether we can even make sense of chemistry's molecules in isolation if there is no structure. So this has also metaphysical implications on the identity of molecules as well. Hopefully we can discuss all this in the questions, but thank you very much. Here's our paper, and today we also have a short reads version of the paper, a small summary, which you can read in case you don't want the whole thing. Thanks.
Thank you very much, Vanessa and Alex. And let's go straight to questions. I believe the first question is from Eugen. Did you want to ask a question? You were the first to say something here. No?
Your microphone, Eugen, open your microphone.
Can you now hear me?
Yes.
Yeah.
Yeah, sorry. Well, I would suggest that I can discuss my comment later with Vanessa and her companion via email.
Okay, thank you.
Definitely.
And Julio has a question.
Okay, is there the underlying assumption that before measurement, a given molecule is there in a classical sense, in a given isomeric state, waiting to be measured? Because then there is some kind of paradox, but it's a false paradox.
You're right. And Alex, do you want to take this or should I?
You can start.
Well, I absolutely agree. And I think that's the point of the paper, to show that we shouldn't expect classical entities and properties. We shouldn't presuppose that there are classical entities and properties prior to measurement and when in isolation, because that's what quantum mechanics tells us, that things are weird before we measure them, right? Alex, do you want to add something to that? Am I right at this, or?
No, yeah, I completely agree. Like before measurement, there's no assumption that there's any kind of determinate molecular structure. In fact, we suggest that some of the literature does make that assumption. And so I think, and maybe Robin will disagree, but there's aspects of Hendry's formalism that involves thinking about, or sort of claims that involve thinking that we need some kind of top-down mechanism for assigning molecular structure, because there isn't molecular structure in isolation from quantum mechanics. And we say, no, there isn't molecular structure in isolation at all. And so we don't need a top-down mechanism to provide it because it's not there.
Mm.
Okay.
Perhaps I would say there are molecular structures, but they are in a superposition state.
Let's move on to Olympia's question, and we can continue in the coffee break, perhaps, on that issue.
Well, I only want to make a comment. Sometimes you talk like a transition from a configurational Hamiltonian to Coulombic or how do you call it? Resultant Hamiltonian. I mean, I want to stress that when you change the Hamiltonian, you change the system. I mean, each system is specified by its Hamiltonian. So you cannot take the eigenfunctions of the configurational Hamiltonian and say that they are components of a superposition of the eigenfunction of the ground state of the resultant Hamiltonian, because you are changing. Brian Sutcliffe says, when you change the Hamiltonian, you change the problem completely. So just my comment that take care about this kind of expressions, and maybe may be confusing. I mean,
I think we agree. I don't see. I think we say the same thing. We do the shift from the resultant to configurational one is a shift from a purely quantum system to one that it has classical kind of features in it, right? Because merely taking the nuclei as being fixed in the configurational Hamiltonian, it's not that you can derive that from the resultant one. You make an abrupt change there, but you do make that change due to the measurement problem that you know, explains why we have the form of the resultant Hamiltonian that we have. So I wouldn't disagree. Why would we disagree on that?
Right, it's like a physical change, right? I mean,
Yeah.
that's what collapse of the wave function involves. The
Yeah.
question is, how do we account for collapse of the wave function? But these are, no one disagrees that there are different systems before and after. If you have a superposed state and then you just find one particular branch of that superposition, that's a different system. Question is, how do we get from one to the other?
Okay.
All right, thank you. And Sharif Mata has a question.
Thank you very much for a thought-provoking talk. I'm not familiar with your paper. I haven't read it, but thank you for the link, Vanessa and Alex. For my simple mind, does it mean if in principle, from the pure point of view, that you have a system that is composed of a superposition of states, and then only the observation collapses one particular state? But in reality, when you have a beaker of cyclooctatetraene, it's cyclooctatetraene is not the probability, it's 100% cyclooctatetraene. It never becomes styrene or anything else. You don't have mixtures of these. So where is what am I missing here? Do you see what I mean? There is the lab reality where you have one of these 8 isomers that you listed, or so. I forgot how many isomers you have listed. But if they are a quantum superposition, then each one comes with a probability amplitude that translated an actual probability of finding it when you measure it. So so that hence my question. Thank you.
Well, I think thank you for this question. I think what your question shows is how vital it is to interpret what we mean by superposition and what we mean by the probabilities, right? Because different interpretations of quantum mechanics are going to understand those superpositions differently, right? Now, whether we should be able to see those superpositions experimentally, I don't think that we should expect that in terms of mixtures, you see, or in terms of waiting long enough time in order for one isomer to switch into another, because that involves already having measurement and the collapse occurring, right?
Just to add, I think that what Julio said in the comments is really important, that we do think that in principle, all states have some kind of probability of tunneling to another state. How should we understand tunneling probabilities? Well, on something like the ever interpretation or collapse interpretations, you think that there really are superpositions, and you think there's just a very, very small amplitude for the other possible configuration. Now we see that, I take it, with enantiomers, with fairly small enantiomers, I take it that it's possible to measure the probability of tunneling for certain examples. But once you get to bigger and bigger molecules, it gets more and more difficult. So while in principle one might think that there's a probability for tunneling from one isomeric configuration to another, that's not the kind of thing that is in fact observed. If it's in a very large system, then it will just be decoherence will be far too quick to allow any such possibility. Or is that so?
Yeah. And I think the closest case is the one in Hund's paradox, right? For chiral molecules, you can actually measure tunneling time, and that was also Hund's solution to the paradox in the first place. But these are types of isomers that have very slight changes, structural changes between them, which makes it easy to kind of measure the tunneling time and see how you go from one to another. Whereas when you go to isomers that differ more deeply in terms of structure, you cannot actually observe these changes, I suppose.
Okay, excuse me for interrupting, but we are slightly over time. Perhaps these questions could be discussed over the coffee break.